Combinatorial Hodge Theory. I'm Dr. Samuel Allen Alexander, mathematician and philosopher, still here, and I'm reading the article Combinatorial Hodge Theory by Christopher Eyre and Matt Larson, published in 2025 in the notices of the AMS. Developed classically in the context of complex geometry, Hodge theory gives certain rigid structures on the cohomology rings of compact Kähler manifolds. In the past few decades, it's been discovered that these structures exist in other contexts as well. Finding such Hodge theoretic structures associated to combinatorial objects has led to remarkable developments, including resolutions of long-standing open problems in combinatorics. Here we give a broad and necessarily incomplete snapshot of these developments in combinatorial Hodge theory. Previous surveys on this topic with more extensive lists of references were published in 2023 and 2024. In section 1, we define the structure colloquially known as the Kähler package and discuss some general principles for its combinatorial applications. These general principles are illustrated in concrete examples. These sections each feature a different combinatorial object, but they follow a common template outlined in section 1.3 so the reader may pick and choose to their taste. In section 5, we outline some strategies common to the proofs of the Kähler package for many different combinatorial structures. The Kähler package. Let us begin with a toy example. Example 1. Let A dot be the polynomial ring reals adjoin xyz modulo the ideal generated by x squared y squared z squared. For each I, the degree I graded component AI as a real vector space has a basis as a real vector space given by the square-free monomials. A0 is the span over the reals of 1, A1 is the span over the rails of xyz, A2 is the span over the rails of xy, yz, and xz, and A3 is the span over the rails of xyz. While the symmetry in the dimensions of the graded components is apparent, there are more refined structures. For example, multiplication by x plus y plus z is an isomorphism from A1 to A2, and multiplication by the cube of x plus y plus z is an isomorphism from A0 to A3. One may recognize the ring in the toy example as the cohomology ring of the cube of CP1. I suppose that's complex projectives, the complex projective line or something? I'm not sure what CP1 is. The example gives a glimpse of the following property, which was first discovered in the cohomology rings of compact Kähler manifolds. Definition. Let A dot be a graded real algebra, the direct sum I equals 0 to d of AI, which is finite dimensional as a real vector space, together with an isomorphism degree from AD, the d part of A, to the reals, and a non-empty open convex cone cal k subset A1. We say that A dot degree cal k satisfy the Kähler package if condition PD. For each 0 less than or equal to I less than or equal to d, the symmetric bilinear form AI cross AD minus I to the rails given by AB maps to degree of A times B is non-degenerate. Condition HL. For each 0 less than or equal to I less than or equal to d over 2 and any L1 dot LD minus 2I in cal k, the map AI to AD minus I given by multiplication by L1 dot LD minus 2I is an isomorphism. HR. For each 0 less than or equal to I less than or equal to d over 2 and any L0 dot LD minus 2I in cal k, the bilinear form AI cross AI to the reals given by the pair AB maps to minus 1 to the I times the degree of A times L1 times dot times LD minus 2I times B is positive definite on the kernel of multiplication by L0 L1 dot LD minus 2I. The reader may verify these properties for the ring in the toy example, where the cone cal k is the set of all AX plus BY plus CZ such that ABC bigger than 0, and the isomorphism degree from A3 to the reals is given by degree of XYZ equals 1. These three properties, PD, HL, and HR, stand for Poincare duality property, Hard-Lefschetz property, and Hodge-Riemann relations, after those who discovered such properties in topology and complex geometry. See Figure 1 for a visualization of the Kähler package. Figure 1. The rows represent the graded components A0, A1, AD. Notice the symmetry. The gray boxes represent the kernel of multiplication by L0 times L1 times dot times LD minus 2I from AI to D minus I plus 1. The PD property implies that the diagram is symmetric. The HL property implies that the diagram monotonically widens towards the middle. HR and HL imply that the signature of the bilinear form AI cross AI to the reals is as illustrated. Remark. One sometimes works with the following more general setup for the Kähler package at the cost of losing the ring structure. That is, instead of a graded real algebra, let A dot be a finite dimensional graded real vector space, direct sum I equals 0 to d AI, together with a symmetric bilinear form degree from A dot cross A d minus dot to the reals, and an open convex subset calc of commuting linear operators L A dot to A dot plus 1 that satisfy degree of L dot dot equals degree of dot L of dot. Then properties PD, HL, and HR can be formulated as before. Geometrically, this more general setup arises when one extends beyond manifolds to study spaces with singularities where a finer invariant than singular cohomology, known as intersection cohomology, is useful. Intersection cohomology in general does not have a ring structure. Suppose now that for a combinatorial object X of dimension D, one can construct a graded real algebra A dot of X equals direct sum I equals 0 to d AI of X that encodes certain combinatorial data about X. Examples of such X and A dot of X will be illustrated in sections 2, 3, and 4. The validity of the Kähler package for A dot of X can then give highly non-trivial information about X. We feature two such ways in the next two subsections. Throughout, suppose A dot equals A dot of X satisfies the Kähler package. The Hard-Lefschetz property and Hilbert functions. Let's consider the Hilbert function, that is, the sequence A0 dot 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 AD of the dimensions AI equals dimension AI of the graded pieces of A dot. Oh, this is confusing. They're using little a's and big A's. So let's read the small a's as little a's because we've been reading the big A's as A's so far. Starting over. Let us consider the Hilbert function, that is, the sequence small a0 dot 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 small ad of the dimensions small ai equals dimension AI of the graded pieces of A dot. Firstly, Poincaré duality implies the symmetry small ai equals small a d minus I for each I in the set 0 through d, but the Hard-Lefschetz property HL implies an even more rigid restriction on the Hilbert function. For any L in calc and I less than or equal to d over 2, the multiplication step L from AI to AI plus 1 must be injective for the multiplication step L d minus 2I AI to A d minus I to be an isomorphism. Therefore, the Hard-Lefschetz property HL implies 1 less than or equal to A, 1 less than or equal to dot 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 less than or equal to A sub floor d over 2, or more strongly, that the sequence of consecutive differences 1, A1 minus 1, A2 minus A1, dot dot dot, A sub floor d over 2 minus A sub floor d over 2 minus 1 is the Hilbert function of the quotient A dot mod ideal generated by L. If, furthermore, A dot is generated as an algebra in degree 1, then A dot mod ideal generated by L is also. Macaulay classified the Hilbert functions of graded algebras which are generated in degree 1 as follows. Given positive integers b and I, one can uniquely write b as b equals ki choose I plus ki minus 1 choose I minus 1 plus dot 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 plus kj choose j for ki bigger than dot 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 bigger than kj bigger than or equal to 1. Dividing b to the Langle I wrangle equals ki plus 1 choose I plus 1 plus dot 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 plus kj plus 1 choose j plus 1. We say that a sequence 1 b1 dot 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 bm is a Macaulay vector or an O sequence if 0 less than or equal to bi plus 1 less than or equal to bi to the Langle I wrangle for all I bigger than or equal to 1. Macaulay showed that 1 b1 dot 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 bm is the Hilbert function of a finite dimensional graded algebra which is generated in degree 1 if and only if it is a Macaulay vector. We deduce that 1, comma, a1 minus 1, comma, a2 minus a1, comma, dot dot dot, comma, a sub floor d over 2 minus a sub floor d over 2 minus 1 is a Macaulay vector. The properties here only require the existence of one element L in A1 satisfying the Hard-Lefschetz property HL. For treatment of commutative rings with such an element, see 2013 paper. Hodge-Riemann relations and log Hodge-Riemann relations and log concavity. Another application of the Kähler package concerns intersection numbers, i.e. numbers obtained by applying the map degree from AD to the reals to certain products of elements in A dot. In particular, for any choice of alpha and beta in A1, one has the sequence M0, M1 dot 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 MD defined by MJ equals the degree of alpha to the J beta to the D minus J. The Hodge-Riemann relations HR with I equals 0 and I equals 1 imply the following properties of this sequence. Proposition. When alpha and beta lie in cal k bar, the closure of cal k in the real vector space A1, the sequence M0 md defined above is non-negative, i.e. mj bigger than or equal to 0 for all 0 less than or equal to j less than or equal to d, is log concave, i.e. mj squared bigger than or equal to mj minus 1 times mj plus 1 for all 1 less than or equal to j less than or equal to d minus 1, and has no internal zeros, i.e. if mj not 0 and mk not 0 for some j less k, then ml not 0 for all j less l less k. In particular, it is unimodal, i.e. m0 less than or equal to dot 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 less than or equal to mk bigger than or equal to mk plus 1 bigger than or equal to dot 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 bigger than or equal to md for some 0 less than or equal to k less than or equal to d. Which reminds us of the monotone increasing shape of that figure 1 above. Anyway, proof. The first two claimed properties are closed conditions, so let's first consider the case where alpha beta in cal k. Then by the Hodge-Lefschetz, or no, not Hodge-Lefschetz, by the HR property, that's the Hodge-Riemann relations, by the Hodge-Riemann relations, property HR with I equals 0 implies that mj equals the degree of 1 times alpha to the j beta to the d minus j times 1, bigger than 0 for all 0 less than or equal to j less than or equal to d. For the log concavity, if alpha and beta are linearly dependent, we have mj squared equals mj minus 1 times mj plus 1 for all j, so assume now that they are linearly independent. For a fixed j, define the bilinear form q from a1 by a1 to the reals by the pair a, b maps to the degree of alpha, define the bilinear form q from a1 cross a1 to the reals by the pair small a, small b maps to the degree of small a times alpha to the j minus 1 times beta to the d minus j minus 1 times small b. Then the Hodge-Riemann property HR with I equals 1 states that Q is negative definite on a codimensional subspace of A1, so Q cannot restrict to be positive definite on the real span of alpha beta. Since MD equals Q of alpha alpha bigger than 0, the restriction of Q to the two-dimensional subspace, the span over the reals of alpha beta, is not negative definite. Hence, we conclude that the determinant of the 2x2 matrix Q of alpha alpha, Q of alpha beta, Q of alpha beta, Q of beta beta is less than or equal to 0, or equivalently that mj minus 1 mj plus 1 minus mj squared is less than or equal to 0 as desired. Lastly, a limit of positive and log concave sequences with no internal zeros is non-negative and log concave with no internal zeros, yielding the desired result when alpha beta in cal k bar. In degrees higher than 1, it is difficult to deduce general inequalities from the Hodge-Riemann relations in a similar way as we have done for the log concavity here. However, the Hodge-Riemann relations in higher degrees are often useful for proving the Hodge-Lefschetz property HL and provide additional restrictions on the structure of A dot. HL is Hodge-Lefschetz, right? Yes, HL is Hodge-Lefschetz. A template. The next three sections will each match the following common template consisting of 5 parts. Objects. What is X? We state the combinatorial objects X of interest. While we are assuming a passing familiarity with them, explicit examples are provided for the uninitiated. Questions. What about X? We discuss questions about X that were resolved by the development of combinatorial Hodge theory for X. Algebras. What is A dot of X? We define the algebra A dot of X that satisfies the Kähler package and explain how it was used to resolve questions about X. Geometric origin. Where is A dot of X from? We explain how, for a certain subset of the object X, the ring A dot of X has a geometric origin as the cohomology ring of a complex projective manifold. And singular objects. How about beyond X? Often there is a natural enlargement of the class of combinatorial objects X, or a different question about X leads to an algebra different from the one featured in Part 3. In both cases, a naive candidate for A dot of X often fails the Kähler package, but we discuss briefly how one can develop a combinatorial intersection cohomology module to amend this failure. Polytopes. Objects. Definition. A polytope, P, in real D space, is a bounded intersection of finitely many closed half spaces. A subset of P is a face of P if it is the locus where a linear functional on real D space achieves its minimum on P, and it is a facet if it is a maximal proper face. We say P is simplicial if every proper face of P is a simplex. Figure 2, two polytopes in real 3 space. The bipyramid, two regular tetrahedra glued along a triangle, on the left is simplicial, but the cube on the right is not. We assume that P is full-dimensional in real D space and primarily consider simplicial polytopes. We point to a 1995 paper as a general reference on polytopes. Questions. Of enduring interest in combinatorics is the structure of the collection of faces of a polytope P. A basic starting point is the number of faces of each dimension. For -1 less than or equal to I less than or equal to D -1, let Fi equals the cardinality of the set of I-dimensional faces of P, with F sub -1 equals 1 for the empty face. The sequence F-1, F0, Fd-1 is called the F vector. For example, in figure 2, the bipyramid has F vector 1, 5, 9, 6, and the cube has F vector 1, 8, 12, 6. An intriguing structure is revealed when one applies the following invertible change of coordinates to the F vector of a polytope. Define the H vector H0 Hd of P by Hk equals sum I equals 0 to k minus 1 to the k minus 1 d minus I choose k minus I Fi minus 1. Equivalently, the H vector is defined by the relation f of t minus 1 equals h of t, where f of t and h of t are the polynomials f of t equals f sub -1 t to the d plus f0 t to the d minus 1 plus plus f sub d minus 1, and h of t equals h0 t to the d plus h1 t to the d minus 1 plus plus hd. For example, the bipyramid has h vector 1, 2, 2, 1, and the cube has h vector 1, 5, minus 1, 1. Let us make two observations from these two examples. We have hd equals 1 for both. Indeed, hd equals 1 holds in general because hd equals -1 to the d minus 1 times sum I equals 0 to d minus 1 to the 1 minus 1 to the I minus 1 Fi minus 1 is the alternating sum of the face numbers, and the reduced Euler characteristic of the boundary of P, which is a d minus 1 dimensional sphere, is -1 to the d minus 1. For the bipyramid, a simplicial polytope, the H vector is positive, symmetric, and unimodal. Do these properties persist for all simplicial polytopes? That is, are H vectors of simplicial polytopes always positive, symmetric, and unimodal? Similar questions about non-simplicial polytopes will be discussed in Part 5. For now, we consider the following conjecture of Macmullen. A sequence H0 Hd of integers is the H vector of a simplicial polytope if and only if it is symmetric, and the sequence H0 H1 minus H0 H sub floor d over 2 minus H sub floor d over 2 minus 1, called the G vector of P, is a Macaulay vector. Note that the condition about the G vector implies the positivity and unimodality of H0 Hd, since H0 equals F sub -1 equals 1. Bilera and Lee showed by explicit construction that if a sequence H0 Hd satisfies the stated conditions, then there exists a simplicial polytope with the sequence as its H vector. For the converse, i.e. that every H vector of a simplicial polytope satisfies these conditions, the proof uses the Kähler package of the following algebra associated with a simplicial polytope P. Algebras. Without loss of generality, translate P so that it contains the origin in its interior. Definition. Let reals adjoin xv such that v a vertex of P be the polynomial ring whose variables are labeled by the vertices of P. Let a dot of P be the quotient ring a dot of P equals reals adjoin xv mod big I plus big J, where big I and big J are ideals defined by big I equals the ideal generated by all products xv1 dot dot xvk such that the set v1 dot dot vk is not a face of P, and big J equals the ideal generated by all sums over v of f of vxv such that f is a linear function on real D space. Note that a dot of P is graded. A key property of a dot of P is that the dimensions of the graded pieces are given by the H vector of P. For example, placing the origin at the center of the base triangle of the bipyramid in figure 2, one finds that in this case a dot of P equals reals adjoin x1 dot dot x5 mod ideal generated by x1, x2, x3, and x4, x5 plus ideal generated by x1 minus x2, x2 minus x3, x4 minus x5, where the variables x1, x2, and x3 correspond to the vertices of the central simplex, and the variables x4 and x5 correspond to the top and bottom vertices. We see that this ring is isomorphic to reals adjoin x1, x4 mod the ideal generated by x1 cubed, x4 squared, whose graded components a0, a1, a2, a3 have bases singleton 1, doubleton x1, x4, doubleton x1 squared, x1, x4, and singleton x1 squared, x4, respectively. Let us further make two observations about a dot of P in general. As AD of P is one-dimensional, since HD equals 1, we may choose an isomorphism degree from AD of P to the reals. There is such a choice, such that for every maximal proper face, big F equals v1 dot dot vd of P, we have degree of x v1 dot dot x vd bigger than 0. The other observation is, let us say that a function phi is piecewise linear if For every proper face big F of P, the function phi is linear on the cone real sub big than or equal to 0 times vi such that I in big F. The degree 1 component A1 of P can be identified with the space of piecewise linear functions modulo the globally linear functions on real D space as follows. Because P is simplicial, each element big D equals some V C V X V in the degree 1 part of reals adjoin XV such that V is a vertex uniquely determines a piecewise linear function phi sub big D by the assignment phi sub big D of V equals CV for every vertex V. Under this correspondence, a linear function f on real D space is associated with sum over V f of V x V, so the generators of the ideal big J correspond to the globally linear functions. We say that L in A1 of P is ample if for every proper face big F of P we can choose a piecewise linear function representing L, which vanishes on big F and is strictly positive on all vertices not contained in big F. The ample elements of A1 of P form an open cone cal K. This cone is non-empty. For instance, consider the piecewise linear function which takes value 1 on each maximal proper face of P. Theorem: let P be a simplicial polytope. The triple A dot of P, degree, cal K, satisfies the Kähler package. Because A dot of P is a graded algebra generated in degree 1, from our discussion above about applications of the Hard-Lefschetz property, we conclude that the H vector is symmetric and the G vector is a Macaulay vector, i.e. Macmillan's conjecture describing the possible H vectors of simplicial polytopes holds. Geometric origin. Stanley proved that A dot of P has the Kähler package by observing that it is the cohomology ring of a projective toric variety. The construction of this toric variety involves perturbing the coordinates of the vertices of P so that they have rational coordinates. This does not change the structure of the faces of P because P is simplicial. This toric variety is in general singular, but the singularities are mild enough that the real PP forms in its cohomology ring still have the Kähler package. Macmillan later gave a purely combinatorial proof that avoids perturbing the coordinates or constructing toric varieties. Singular objects. For non-simplicial polytopes, the H vector no longer has the pleasant properties of the H vector of simplicial polytopes. For example, we saw that the H vector 1, 5, minus 1, 1 of the cube is no longer a non-negative. Instead, one should consider the toric H vector, which is a combinatorial invariant of a polytope P, which is recursively defined in terms of the poset of faces of P. When P is simplicial, it agrees with the H vector. The toric H vector of the three-dimensional cube is 1, 5, 5, 1. When the polytope has vertices with rational coordinates, the toric H vector records the dimensions of the graded pieces of the intersection cohomology of the associated projective toric variety. The Hard-Lefschetz theorem for intersection cohomology implies that the toric H vector is symmetric and unimodal. For arbitrary polytopes, it may not be possible to perturb the vertices so that they have rational coordinates without changing the structure of the poset of faces, so there may be no associated toric variety. Nevertheless, Karu showed that the toric H vector is symmetric and unimodal. He proved this by verifying the diversion of the Kähler package as formulated in Remark 3 holds for an analog of the intersection cohomology of a projective toric variety. Next, we talk about Bruchhaus spaces, objects. Let V be a finite-dimensional real vector space with an inner product. For a hyperplane H subset V through the origin, the reflection across H defines an automorphism SH of V. Definition: a finite Cox-Sitter group big W represented on V, a finite Cox-Sitter group W represented on V, is a subgroup of general linear V generated by the set of reflections SH, H in cal H, where cal H is a finite set of hyperplanes in V satisfying SH of cal H equals cal H for all H in cal H. We point to a paper from 1990 as a general reference on Cox-Sitter groups. Example: with a standard inner product on real n space, the symmetric group frac Sn, symmetric group of 1 through n, is a finite Cox-Sitter group represented on real n space with cal H equals the set of Hij such that 1 less than or equal to I less j less than or equal to n, where Hij equals the set of R in real n space such that xi equals xj. Among the remarkably rich combinatorics of a finite Cox-Sitter group is its poset structure, described as follows. Fix any connected component cal K in the complement V minus union H in cal HH of the hyperplanes. The connected component is an open cone whose closure has exactly R equals dimension of V minus dimension of intersect cal H many facets. Let big S equals S1 dot dot SR subset W be the reflections by these facet hyperplanes called simple reflections. Any small w in W is a product of simple reflections. Let L of small w denote the minimum number of for which one can write small w equals small si1 dot dot small si L of small w, called the length of small w. Definition: the Brouillard poset of big W. Brouillard poset of big W is a poset on big W defined as the transitive closure of the relation small w1 less small w2 if and only if L of small w2 equals L of small w1 plus 1 and small w2 equals small s big H small w1 for some big H in cal H. Two facts about the Brouillard poset follow. The Brouillard poset has a unique minimal element 0 hat, which is the identity, and a unique maximal element called the longest element and denoted small w0. Let D equals L of small w0. The Brouillard poset is a graded poset graded by the length L. That is, for all small w and big W, every maximal chain in the closed interval from identity to small w has L of small w plus 1 elements. Remark: the group big W acts freely and transitively on the set of connected components of the hyperplane arrangement complement V minus the unit of cal H. We may thus label the components by big W with cal K labeled by the identity and a component C by the unique small w and big W, such as C equals small w times cal K. Then the length L of small w and big W is the minimum number of hyperplanes that a path from cal K to the component small w dot cal K must cross. Figure 3, diagram of the Brouillard poset of the symmetric group on 4 characters. Looks like a crystal. Example: returning to the previous example of the symmetric group on n represented by real n space, let cal K equals the set of x in real n space such that x1 bigger than dot 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 bigger than xn. The simple reflections small si, 1 less than or equal to I less than or equal to n minus 1, correspond to adjacent transpositions, transpose I with I plus 1. Moreover, one can show, for instance, using remark 11, that the length of a permutation small w in the symmetric group on n characters is length of small w equals the cardinality of the set of pairs ij such that 1 less than or equal to I less j less than or equal to n and small w of I bigger than small w of j, the number of inversions of small w. The Brouillard poset of the symmetric group on 4 characters is illustrated in figure 3. That was the crystal we saw. Questions. Given a graded poset with a unique minimum 0 hat, like the Brouillard poset of big W, we may consider its graded components. For I bigger than or equal to 0, let Pi equals the set of P in the graded poset such that a maximal chain 0 hat less than dot 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 less than P consists of I plus 1 elements, and that Pi equals cardinal of cal Pi. A question of enduring interest for a graded poset concerns the Sperner property. Is the maximum cardinality of an antichain, i.e. a subset consisting of pairwise incomparable elements in cal P, equal to the maximum of the set P0 dot 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 PD? We may further ask whether cal P is strongly Sperner. For each 0 less than or equal to I less than or equal to D over 2, is there a collection of Pi many pairwise disjoint chains of the form xi less xi plus 1 less dot 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 less xd minus 1 with xi in cal Pi and xd minus 1 in cal PD minus 1? The reader may verify as an exercise that the stated strongly Sperner property indeed implies the Sperner property. Note also that the strongly Sperner property implies that P0 dot 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 PD is symmetric and unimodal. We explain how these questions can be answered in the case where cal P equals cal P of big W, a Brouillard poset, by considering a graded algebra constructed from big W. Algebras. Let sim dot of big V be the graded algebra of polynomials generated by a basis of big V. The group big W acts on it via its action on big V, so we may consider the ideal big I big W plus generated by the positive degree big W invariant polynomials f in sim bigger than 0 of big V such that W times f equals f for all W in big W. Definition. The co-invariant algebra of big W is the quotient a dot of big W equals sim dot of big V mod big I big W plus. One finds the following properties of the co-invariant algebra from results of Bernstein, Galfond, and Galfond. There exists a collection of polynomials Pw in sim dot of big V such a W in big W that forms a vector space basis in a dot of W, satisfying degree of Pw equals L of W for all W in big W. We call this basis the Schubert basis of A dot of big W. Abusing notation, we write calc K also for the image in A1 of big W of the connected region calc K subset big V. This image is a non-empty open cone. For big L in calc K, the Schubert basis big B W of A dot of W satisfies the property that big B W is a linear combination of big P U, where U bigger than or equal to W. By property 1, the existence of the collection of polynomials, we may choose an isomorphism degree from AD of big W to the reals such that degree of big P W is 0 bigger than 0. Theorem: the triple A dot of big W calc K degree satisfies the Kähler package. Combining the property 1 above with the Hodge-Lefschetz property of A dot of big W implies that P0 dot dot PD is symmetric and unimodal. Moreover, Stanley observed that combining property 2 with the Hodge-Lefschetz property leads to the Strongly-Sperner property of calc P equals calc P of big W as follows. The big L in calc K for each 0 less than or equal to j less than or equal to d, the Schubert basis realizes multiplication by HA of big W maps with a dot big L over to AJ plus 1 of big W as a PJ plus 1 cross PJ matrix denoted big L super J. Denote by big L super J sub big I big J the submatrix of big L super J for subset big I of the rows and a subset big J of the columns. Then for 0 less than or equal to I less than or equal to d, the Cauchy-Binet formula gives determinant of big L super d minus I minus 1 times dot 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 times big L super I plus 1 times big L super I equals sum big I dot 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 big I d I minus equals sum big I sub I dot 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 big I sub d minus I product j equals I to d minus I minus 1 determinant big L super j sub big I j plus 1 big I j, where the summation is over all sequences of subsets such that pi equals cardinal of big I sub I equals dot 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 equals cardinal of big I sub d minus I. As big L d minus 2I from big A I of big W to A d minus I of big W is an isomorphism, the left-hand side above is non-zero, so that a summand in the right-hand side is non-zero for some big I sub I dot dot big I sub d minus I. In particular, each square matrix big L super j sub big I j plus 1 has a permutation pattern with all non-zero entries, which gives a sequence of matchings between calc j and calc j plus 1 for all j. That these matchings respect the order on calc follows from the property 2 above. That was the property about the image of a certain function being a non-empty open cone. Example: when big W is the symmetric group on n characters, we have sim dot of real n space equals reals adjoin x1 dot 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 xn. A particular set of representatives for the Schubert basis of A dot of the symmetric group on n characters called Schubert polynomials is given by the following rule. First, one sets big Pw0 equals x1 to the n minus 1 times x2 to the n minus 2 times dot 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 times xn minus 1. And whenever W of I bigger than W of I plus 1, one sets big P sub WSI equals partial sub I of big PW, where partial sub I is an operator on reals adjoin x1 dot 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 xn defined by partial sub I f equals f minus si dot f quantity over xi minus xi plus 1. I wish they would tell us how they want us to pronounce that partial symbol. Anyway, for example, when n equals 3, we have A dot of the symmetric group on 3 characters equals reals adjoin x1, x2, x3 mod the ideal generated by x1 plus x2 plus x3, comma x1, x2 plus x2, x3 plus x1, x3, comma x1, x2, x3, and the elements 1, x1, x1 plus x2, x1 squared, x1, x2, x1 squared, x2 of A dot of the symmetric group on 3 characters form the Schubert basis. Remark: using similar methods, the results here for the Brouillard-Post set calc P of big W can be extended to the Brouillard-Post set calc P of big W mod big W sub big J on the set of cosets of a parabolic subgroup big W big J of big W. For classical types A, B, C, and D, the Strongly-Sperner property of calc P of big W admits an elementary proof, but this elementary method does not extend to the parabolic case. Geometric origin. When big W satisfies an integrality condition of being crystallographic, it is of the Weyl group of a complex semi-simple Lie group big G. In this case, Borel showed that the covariant algebra A dot of big W is the cohomology ring of the flag variety big G mod big B, which is a smooth projective variety. Thus, the Kähler package for A dot of big W follows from classical Hodge theory in this case. The Schubert basis for A dot of big W comes from the Brouillard decomposition of big G mod big B. It is a stratification of big G mod big B into affine cells, whose closures in big G mod big B thereby defines a basis for the cohomology ring. Bernstein, Gelfand showed how to interpret this geometric basis for A dot of big W purely algebraically. For non-crystallographic finite Coxeter groups where a Lie group Big J is no longer available, Elias and Williamson established the Kähler package in a much more general setting of Zergel bimodules, which we discuss in the next part. Singular objects. For an element W in big W, we consider the interval, closed interval from identity to W of cal P of big W. Let us denote cal P equals closed interval from identity to W. We may ask similar questions for the interval cal P as we did for the whole poset cal P of big W. However, a graded algebra with a basis labeled by the elements of the interval cannot in general satisfy the Kähler package. The cardinalities of the graded components of the closed interval from identity to W are often not even symmetric. For example, when big W is the symmetric group on 4 characters, the sequence P0 ... P4 for the interval reads 1, 3, 5, 4, 1. Geometrically, when big W is the Weil group of a Lie group big G, this failure is reflected in the fact that the variety under concern is the Schubert variety big XW of W and big W, which is in general singular. This singular variety admits a particular desingularization known as the Bott-Samuelson resolution. Extracting key algebraic and combinatorial features of this desingularization leads to Zergel bimodules, which Elias and Williamson showed satisfy the Kähler packages formulated in Remark 3. Combining this with observations made by Björner and Ekdahl, originally made only for Weil groups, one can show that the interval from identity to W satisfies a weak version of the Sperner property. For every 0 less than I less than L of W over 2, there exists an injection M from cal P I into cal P sub L of W minus I, such that W less than M of W. The next big family of examples is matroids. Objects. Let big E equals 1 through n be a finite set. Definition. A matroid big M on big E consists of a non-empty set cal I of subsets of big E called the independent sets of big M, satisfying 2 properties. If big I in cal I and big J is subset big I, then big I in cal I, and if big I big J in cal I, the first property is if big I in cal I and big J subset big I, then big J in cal I, so cal I is closed downward. And the second one is if big I big J in cal I with cardinal big I less than cardinal big J, then big I union singleton J in cal I for some J in big J minus big I. What does this say? If you have a small element and a big element, then you can take some element of the big element, not in the small element, add it to the small element, and remain in the matroid. Maximal elements of cal I have a common cardinality, which is called the rank R of big M. To avoid trivialities, we suppose that big M is loopless, i.e. that every one element subset is independent. We point to a 1971 paper as a general reference on matroids. Figure 4, a finite graph big G and a matrix representing a subspace of blackboard bolt K to the 4th on its row span. The matroids associated with each are identical. Example, let big G be a finite graph with edges big E such as the one illustrated in figure 4. Then the set cal I equals the set of subsets of big E which do not contain cycles is the set of independent sets of a matroid. Such matroids are called graphical matroids. Example, let big L subset a field K to the big E be a vector subspace over a field K. Then the set cal I equals the set of big I subset big E such that the composition big L into K to the E into K to big I is surjective is the set of independent sets of a matroid. Concretely, if big L is the row span of an R by big E matrix, then cal I consists of linearly independent subsets of the column vectors VE such as D and big E. Such matroids are called linear or realizable matroids. We caution that while graphs and linear subspaces are 2 prototypical sources of matroids, almost every matroid in some precise sense does not arise in this way. Questions. We consider 2 sequences of numerical variants of a matroid big M over rank R. First, let big I0 of big M big IR of big M be the sequence that counts the number of independent sets according to their cardinality, that is, big IK of big M equals the cardinal of the set of big I and cal I such that big I equals K. For the second sequence, to find the rank function RK big M by rank big M. For the second sequence, to find the rank function rank big M by rank big M of big S equals the maximum of the cardinal of big I such that big I subset big S and big I and cal I. For subset big S subset big E, Then we define W0 of big M dot dot WR of big M by WK of big M equals summation over big L subsets big S of big E such that rank big M of big S is K minus 1 to the card big S plus K, which counts the subsets of the same rank with signs according to their cardinality. This sequence arises naturally in graph theory as follows, that big M be the matroid of a finite connected graph big G with edges big E on R plus 1 vertices. A proper coloring of big G is a coloring of its vertices such that no incident vertices share the same color. Then its chromatic polynomial over big G of Q equals the number of proper colorings of big G with at most Q colors, is related to the sequence WK of big M by chromatic color of Q over big G all over Q equals omega 0 equals W0 of big M Q to the R minus W1 of big M Q to the R minus 1 plus dot plus minus 1 to the R WR of big M. Example, the reader may check that in the matroid of the graph in figure 4 we have big I0 of big M, big I1 of big M, big I2 of big M, big I3 of big M equals 1, 4, 6, 3, and W0 of big M, W1 of big M, W2 of big M, W3 of big M equals 1, 4, 5, 2. Long-standing conjectures from the 70s by various matroid theorists including Mason, Rota, Heron, and Welsh stated the following. Both the sequences big I0 of big M big IR of big M and W0 of big M WR of big M are log concave with no internal zeros. Both and more related conjectures were recently resolved by establishing the Kähler package for some algebras related to matroids as we'll now describe. Algebras. To define the algebra associated with the matroid big M, we need the following notion. A subset big F subset big E is said to be a flat of big M if it is the maximal subset of big E of given rank, i.e. if rank big M of big F union E bigger than rank big M of big F for all E in big E / big F. Definition. The Chow ring of a matroid big M with real coefficients is the graded real algebra A dot of big M equals direct sum I equals 0 to R minus 1 AI of big M defined as the following quotient of a standard graded polynomial ring. A dot of big M equals reals adjoint X big F such big F is a non-empty flat of big M, all divided by big I plus big J, where big I is the ideal generated by X big F prime such that big F subset big F prime and big F prime not such that big F is not subset big F prime and big F prime not subset big F. And big J is the set of sums big F containing I, X big F such that I and big E. Let Calk be the set of elements Xi in big A1. Let Calk be the set of elements Xi in A1 of big M, they can be written as Xi equals some empty set proper subset of big F proper subset of big E, C of big F, X big F for some function C, 2 to the big E to the reals, satisfying C of empty set equals C of big E equals 0, and C of big S1 plus C of big S2 bigger than C of big S1 intersect big S2 plus C of big S1 union big S2 for all big S1 big S2 subset big E. Since the sum of two such functions retains this property, the set Calk is an open convex cone in A1 of big M, which is non-empty. For instance, let C of big S equals cardinal big S times cardinal big E / big S. A recent breakthrough in matroid theory by Adi Prosito, Ha, and Katz states that the Chow ring of a matroid satisfies the Kähler package. Theorem. There is an isomorphism degree big M from AR minus 1 of big M to the reals defined by the property that the degree of minus X big E quantity to the R minus 1 equals 1. The triple A dot of big M, Calk, degree big M, satisfies the Kähler package. To use the Kähler package of A dot of big M to deduce properties about the sequence W0 of big M WR of big M, we need the following theorem of Ha and Katz. Let W0 bar of big M WR minus 1 bar of big M be the sequence defined by the property Wi of big M equals Wi bar of big M plus Wi minus 1 bar of big M for all I equals 0 through R, with W minus 1 bar of big M equals W bar of big M equals 0. Theorem. Let alpha and beta be elements of A1 of big M defined by alpha equals minus X big E and beta equals some 0 and beta equals some empty set proper subset of big F proper subset of big E X big F. Then for I equals 0 through R minus 1 we have that degree over big M of alpha to the R minus 1 minus I beta to the I equals Wi bar of big M. Because the elements alpha and beta are in the closure of Calk, we thus conclude that W0 bar of big M WR minus 1 bar of big M is log concave with no internal zeros. The relation Wi of big M equals Wi bar of big M plus Wi minus 1 bar of big M then easily implies that W0 of big M WR of big M is log concave with no internal zeros. Because the sequence big I0 of big M big IR of big M can be realized as the sequence W0 bar of big M prime WR bar of big M prime, where big M prime is the free coextension matroid of big M, it is also log concave with no internal zeros. Geometric origin. When big M is the matroid of a linear subspace, big L subset complexes to the big E, the algebra A dot of big M is the cohomology ring of a complex smooth projective variety known as the wonderful compactification big W big L of a hyperplane arrangement complement introduced by De Contini and Procesi. Thus, in this case, the Kähler package for A dot of big M follows from classical Hodge theory. Moreover, let us indicate a geometric origin for the formula degree big M of alpha to the I minus 1 minus I beta to the I equals Wi bar of big M. Considered as elements in the cohomology ring of big W big L, the elements alpha and beta are divisor classes that define a map to a projective space. For beta, the associated map V big W big L to projective space of complex big E space has the image known as the reciprocal linear space, whose degree was known to be WR minus 1 bar of big M. Singular objects. Let us consider another numerical invariant of big M. Define the sequence big W is 0 of big M dot dot big W R of big M by big W K of big M equals the number of rank K flats of big M. Equivalently, let cal P of big M be the positive flats of big M ordered by inclusion, which is graded by rank. Let cal P K of big M be the kth graded component of cal P of big M, i.e. the set of rank K flats of big M, so that big W K of big M equals cardinal of cal P K of big M. It's conjectured but unknown whether this sequence is log concave. Dowling and Wilson conjectured a related but different property, namely that the sequence is top-heavy, i.e. big W I of big M less rank of big W R minus I of big M for all I less rank of D over 2. More strongly, one may conjecture that there is an injection Mi from cal Pi of big M to cal Pr minus I of big M for each I, such that Mi of big F superset big F for all big F in cal Pi of big M. The resolution of this conjecture by Braden, Ha, Mathern, Proudfoot, and Wang is featured in an upcoming What Is Notices of the AMS survey. Let us give a rough sketch here. As the question is about the graded poset cal P of big M, taking an inspiration from the previous discussion about the strongly Sperner property for Brouillard posets, one may seek an algebra whose basis is naturally labeled by the flats of big M. Among possibly many such algebras, we consider the following one. Definition: the graded Mobius algebra of a matroid big M is a graded real algebra B dot of big M equals direct sum I equals 0 to R Bi of big M, whose ith graded component Bi of big M is the vector space with basis y big F such a big F in cal Pk of big M, and with multiplication y big F times y big G equals y big F v big G if rank big M of big F v big G equals rank big M of big F plus rank big M of big G, and 0 otherwise, where big F v big G denotes the unique minimal flat of big M containing both big F and big G. The graded Mobius algebra generally fails to have the Kähler package. The dimensions of its graded pieces are usually not even symmetric. Geometrically, this failure reflects that when big M is the matroid of a linear subspace big L subset complex big E space, the graded Mobius algebra is the cohomology ring of a singular projective complex variety called the matroid-Schubert variety, which is the closure of big L in CP1 quantity to the n. This singular variety admits a particular desingularization known as the augmented wonderful compactification. By extracting key algebraic and combinatorial features of this desingularization, one can construct the intersection cohomology module IH dot of big M, which is graded B dot of big M module with an injection B dot of big M into IH dot of big M. Then, with significant effort, Braden, Ha, Mathern, Proudfoot, and Wang show that IH dot of big M satisfies the Kähler package with cal K consisting of linear operators L, IH dot of big M to IH dot plus 1 of big M, given by L equals multiplication by some I in big E, AI, YI, where AI bigger than 0 for all I in big E. Then, since B dot of big M is a submodule of IH dot of big M using arguments similar to the one outlined in section 3, one can conclude that there is an injection Mi from cal Pi of big M to cal P R minus I of big M, such that for each I, Mi of big F superset big F. In particular, this proves the top-heavy conjecture of Dowling and Wilson. Proving the Kähler package. It's usually very difficult to prove that an algebra has the Kähler package. For the cohomology ring of a complex Kähler manifold or a complex projective manifold, the Kähler package is usually proved by analytic methods. However, analytic methods seem not suitable for the combinatorial settings described above. In each of the three settings, classical Hodge theory can be used for a subset of the combinatorial objects that arise geometrically, but establishing the Kähler package in general requires an intricate analysis of combinatorics specific to each setting. Nonetheless, there's a basic inductive strategy common to all three settings, first introduced in the case of simplicial polytopes by Macmullen. It roughly consists of 3 steps. 1. First, prove PD. What was PD? PD is Poincare duality. So 1. First, prove Poincare duality by some direct argument. For example, often it is possible to compute a basis so that the matrix representing the pairing is upper triangular. 2. One then proves Hard-Lefschetz for all choices of elements of cal K by inductively assuming Hodge-Riemann in lower dimensions. And 3. By Hard-Lefschetz and continuity, one then needs to verify Hodge-Riemann for a single choice of an element in cal K, often via another layer of induction. We illustrate step 2, proving Hard-Lefschetz for all choices of elements of cal K by inductively assuming Hodge-Riemann in lower dimensions. In the case of simplicial polytopes, let P be a d-dimensional simplicial polytope in real D space which contains the origin in its interior. For each vertex V of P, let PV be the polytope in real D space mod reals times V, formed by taking the convex hull of the images of the vertices W such that the doubleton VW is an edge of P. We may assume that the Kähler package holds for A dot of PV by induction on the dimension. There is a restriction map phi from A dot of big P to A dot of big PV such which has the property that phi v of L is ample, as defined above if L in A1 of P is ample. When the degree map on A dot of PV is normalized appropriately, this map satisfies degree P of A dot xv equals degree PV of phi v of A. Since the dimension of AIP equals the dimension of A d minus I of P by the Poincare whatever, PD. What was PD? PD was Poincare duality property. Since dimension AI of P equals dimension A d minus I of P by the Poincare duality property, in order to prove hard Lefschetz for A dot of P, it suffices to show that for each I less than or equal to d over 2 and L1 dot dot LD minus 2I ample, the map AI of P to AD minus I of P given by multiplication by L1 dot dot LD minus 2I is injective. Suppose A in AI of P is the kernel of this map. Because L1 is ample, we can write L1 equals sum CV xv, where CV bigger than 0 for each vertex V. We then have 0 equals the degree over P of A squared L1 dot dot LD minus 2I equals sum over V of CV degree P of A squared xv L2 dot dot LD minus 2I equals sum over V CV degree PV of VV of A squared VV of L2 dot dot VV of LD minus 2I. By construction, VV of A, VV of L1, VV of L2 dot dot VV of LD minus 2I equals 0. Therefore, by Hodge-Riemann for A dot of PV, we have minus 1 to the I times the degree over PV of VV of A squared VV of L2 dot dot VV of LD minus 2I is bigger than or equal to 0, with equality if and only if VV of A is 0. We therefore must have VV of A is 0 for all V. Then the Poincare duality property implies that A equals 0. After a variation of this argument is used to prove hard Lefschetz for A dot, it remains to carry out step 3 and verify Hodge-Riemann. As the signature of a family of non-degenerate bilinear forms is constant, a continuity argument and hard Lefschetz for A dot shows that it suffices to verify the Hodge-Riemann relations for a single choice of Li. To do this, typically one finds a filtration A0 dot subset subset AK dot equals A dot, where each AI dot is equipped with a cone cal I and an isomorphism degree I from A di to the reals. The ring A dot 0 is very simple and one can verify by hand that Hodge-Riemann holds for it. One attempts to prove that the Kähler package holds for A dot I by induction on I. We typically have cal Ki subset cal Ki plus 1 bar and A dot I plus 1 into A dot I direct sum A dot I plus 1 mod A dot I as A dot I modules. Often this direct sum decomposition can be chosen to be orthogonal with respect to the bilinear form, where small a small b maps to a degree I plus 1 of small a times L to the d minus 2k times small b on a ki plus 1 for any L in cal ki. One understands the signature of this bilinear form on A dot I by induction, and one attempts to relate the module A dot I plus 1 mod A dot I to objects of lower dimension. Using this, one attempts to show that the restriction of this bilinear form to A dot I plus 1 mod A dot I is non-degenerate and has the correct signature, verifying Hodge-Riemann for L. In the case of polytopes, one uses a version of the weak factorization theorem, which states that one can obtain any simplicial polytope from the simplex by a series of simple combinatorial operations. One verifies that Hodge-Riemann is preserved under these operations. This reduces to verifying Hodge-Riemann for the case of a simplex, which can be done directly. Lastly, we mentioned that one can extend the validity of the Kähler package to singular cases. An inductive strategy for doing so in the case of complex projective varieties can be found in a 2005 paper. Acknowledgements. We thank Ben Elias, Eric Katz, Jacob Mathern, Chris McDaniel, Han Moon, Richard Stanley, and the referees for helpful comments on an earlier version of this article. Well, that's very interesting. It's an exceedingly difficult paper to follow, but the basic structure is very interesting, and what's remarkable is that so many different seeming things in combinatorics and so many different seeming open problems are all solved using this same technique. And I also appreciate the inductive proof there at the end. It's a very interesting structured induction where you have this structure and you assume all the properties hold for the small thing and you use that to get a particular property of the next level, and then you finish that next level and then you go up the ladder. Anyway, I'm Dr. Samuel Allen Alexander, mathematician and philosopher. Please like, comment, and subscribe. I'll see you in the next video.